In this lesson, we will learn how we can apply the central limit theorem when working with the problems involving sample mean. According to records, the amount of precipitation in a certain city on a November day has a mean of 10 inches with a standard deviation of 700 inches. What is the probability that the mean daily precipitation will be 105,000 inches or more for a random sample of 40 November days, taking over many years? Carry your intermediate computations to at least 4 decimal places and round your answer to at least 3 decimal places. What I know from the given story is the following: that for this population, mean is 10/100th, sigma is 7/100th, and we have a sample of size 40. We do not know anything about the distribution to be normal for the population. We are not told that it's normal. However, according to the central limit theorem, even if we work with a population that is not normally distributed, we know that if we sample the population long enough and then produce the distribution of sample means, we will get a normal distribution. The central limit theorem states that the mean of that distribution of sample means will be equal to the mean of the population, which is same as we had here, 10/100th. The standard deviation of the sample mean will be the standard deviation of the population divided by the square root of the sample size. In our case, it is 40. Knowing this information and knowing that the sample means will be normally distributed, I am allowed to use the normal CDF function using these parameters for my random samples. So, probability that sample mean will be greater than or equal to 0.105 will be equal to normal CDF on the interval from 105 thousandths to positive infinity, because my interval starts from 0.105 and goes on forever to the right side. Sample mean of 10/100th and standard deviation of 700 divided by square root of 40. This number probably will not come out to be very nice, and you could compute this quantity and round to 4 decimal places because that's your intermediate computation. I typically enter this as it is in its exact form into the calculator, and that produces 0.326 rounded to 3 decimal places. Let's take a look at one more example. The producer of a weight loss pill advertises that people who use the pill lose after 1 week an average, which is mean, of 1.8 pounds with a standard deviation of 1.05 pounds. In a recent study, a group of 60 people who used this pill were interviewed. The study revealed that the people lost a mean of 1.92 pounds after 1 week. If the producer's claim is correct, what is the probability that the mean weight loss after 1 week on this pill for a random sample of 60 individuals will be 1.92 pounds or more? Again, carry your intermediate computations to at least 4 decimal places. Round your answer to at least 3 decimal places. First of all, I will be extracting the information I am provided. I know that the mean is 1.8 pounds. Standard deviation is 1.05 pounds. And the sample we had consists of 60 people. Please notice that our solution will be based on the assumption that producer's claim is correct, which means we can use this as our population parameters. Using the central limit theorem, I can compute mu sub x bar to be the same thing as mu itself, 1.8. I can find sigma sub x bar to be the standard deviation of the population divided by the square root of sample size of 60. And we need to make sure that the sample size is large enough for this to work. And it is. 60 is pretty big size. We want at least 30. Probability that the sample mean will have a value of at least 1.92, which means x bar will be greater than or equal to 1.92, is normal CDF of 1.92 to positive infinity with the mean of 1.8 and standard deviation of 1.05 divided by square root of 60. When you enter all of that into your calculator, you should get 0.188 when rounded to 3 decimal places.